Hey everybody, it's Thursday, January 14th, and as you can see here in the aim today, our goal for today's video is to review basic problem solving techniques for work, energy, and power problems. And we're going to do this by going over all of the answers to all of the problems on both of the sheets that were assigned to you yesterday. Now, because there are a good amount of problems on both of these sheets, I want to just get into this straight away. And so we're going to start with the first problem on the sheet that was entitled Work and Energy Problem Solving Worksheet, where this was the first problem. This first problem here says a 1500 Newton crate sits at rest on the floor. How much work is required to move the crate at a constant speed, 6.5 meters against the force of friction of 500 newtons, and 6.5 meters vertically? So the first thing to realize here, and we'll write a note about this after we go over the solution, the first thing to realize about this problem here is that they are telling you that the crate is being moved at a constant speed. The fact that the crate is being moved at a constant speed is very important, particularly for this first one, because that gives you information, A, about the size of the force that's being used to push on the crate, and B, it's giving you an insight into what's happening with the energy here in this problem. According to the work-energy theorem, which is not actually required to solve the problem, but just to really understand what's going on, the work done on the crate is equal to the change in energy. But of course, because this crate is being moved on a level floor at a constant speed, the crate itself is not actually gaining any energy. It's important to realize that if the crate was not continuously pushed with an applied force, the crate would be losing energy. And so the work that's being done here is simply preventing friction from taking away energy from the object. In that sense, we usually refer to this as the work that's done against friction. Essentially, what's happening is that we're putting that energy in, and friction is immediately taking it out and converting it to heat. The crate itself is not actually gaining energy, which we can tell because it's moving at a constant speed. For part B, the fact that the crate is being lifted vertically at a constant speed tells us the forces acting in the vertical direction cancel. And so that means the force we're opposing in this case is not that friction force, but rather is the force of gravity, or the weight of the crate, which is given here in the problem. So let's start with part A. Part A here says the friction force acting on the crate is 500 newtons. And since we're pushing this thing at a constant speed, the force we're applying is equal to the force of friction, which is 500 newtons. You could label that as force applied if you want, but since the equation since the work equation contains just the symbol F, I'm just going to label it as F here, really, though it's no big deal. Delta X here, the displacement of the crate, is told to us in the problem to be 6.5 meters. The angle between the krate's displacement and the force is 0 degrees, and the work is our unknown. Now, we know the work done here involves a 0 degree angle because they do not give us any information otherwise. And of course, if the thing is in fact moving on a level floor, and its displacement is parallel to the surface, we know that the friction force is parallel to the surface, and so the force opposing it is going to be parallel to the surface as well. And so that means here that the applied force definitely is parallel to the displacement because it's parallel to the surface. So to calculate the work here, we just use the work equation, F delta X cosine theta. Of course, the cosine of 0 degrees is 1, so we can just get rid of that, and that means the work here is just going to be the product of the force and the displacement. So we have our 500 Newton force multiplied by our 6.5 meter displacement, and that's going to give us a work value of 3250 Newton meters, or 3,250 joules. And that's it for part A. For part B, the force here that we're applying to lift the crate vertically is going to be equal and opposite to the weight of the object, which is 1,500 newtons. And of course here, the displacement that's experienced by the crate is going to be that same 6.5 meters. And again, if we are lifting the crate vertically this time, that means the displacement of the crate is vertical, And because we are opposing the force of gravity, the force that we are applying to lift the crate is directly upward or parallel to the displacement. So once again, that makes the angle 0. And then we're looking for the work. So work is equal to F delta X cosine theta, according to your AP Physics reference table. The cosine of 0 degrees is 1, so we just get rid of that. And once again, we're multiplying the force and the displacement. So we have 1,500 newtons multiplied by our displacement of 6.5 meters. And the work done in this instance is 9750 joules. Now, we already mentioned for part A that the work being done is not actually increasing the energy of the crate because the crate is moving at a constant speed and it's moving on a level surface. However, in part B, the work that's being done is lifting up the object and changing the height of the object. And so that means here that this value for the work, 9750, is the change in the gravitational potential energy of the crate. Now, they don't actually ask you that, but that's an important point nonetheless. Let's just take a second and write down a quick note about this problem because these kinds of situations come up often. So we'll say here, note, when moving an object at a constant speed, the force you need to use in the work equation is always equal and opposite the force that's opposing the motion. And so in case A, the force applied must be equal to the force of kinetic friction for the object to move at a constant speed. And in case B, the force applied must be equal to the downward force of gravity in order for the object to be lifted at a constant speed. Take a second to pause this video here and write that down. When you hit play, we'll move on to number 2. Okay, number 2 is a question with many parts, and so we're just going to do it 2 parts at a time here. It says a baseball with a mass of 160 grams traveling at 40 meters per second moves a fielder's glove backward 35 centimeters when the ball is caught. So the ball is traveling at 40 meters per second. It collides with the glove, and the glove moves backward 35 centimeters when it's slowing down the ball until it finally stops when it's officially caught by the person catching it. The question says, what was the average force exerted by the ball on the glove? I like this kind of question because it's the kind of question that sort of relates energy stuff to dynamic stuff through kinematics. And so this kind of problem really highlights the connections between all of these different methods for analyzing the motion of an object. And the AP course, of course, as we've mentioned many times, is really all about the bigger picture here involved in these situations. So part A is asking us how can we describe the relationship between force and work, and part B is asking us how we can describe the relationship between work done on the ball and the speed of the ball. So we can say here, for this question, at least for part A, again, the question says how can we describe the relationship between the force and work, and we can say here the work done on the ball is directly proportional to the force exerted on the ball. And that, of course, is because the equation says the work is equal to FD, or F delta X, cosine theta. Pretty straightforward answer. The work done is directly proportional to the force. More force, more work. That's it. Part B, on the other hand, is a little more complicated because it says, what is the relationship between the work done on the ball and the speed on the ball? And I think this question is important because it highlights basically the only 2 ways you need to ever think about work. The first way you should think about work is that it's just F delta X times cosine theta. The second way you should be thinking about work is that the work done on the ball is equal to the change in the ball's kinetic energy. And that's according to the work energy theorem, which of course says that the work is equal to the change in total energy. So that's how we sort of connect work and kinematics through the speed of the object here. So we could say, since the kinetic energy of an object is directly proportional to the square of the object's speed, the work is directly proportional to the difference in the squares of the object's initial and final speeds. And if you're a little confused or unclear about why I'm saying the difference in the squares, it's because, well, if work is equal to the change in energy, then the equation would read 1/2 m times v final squared minus v initial squared. And so the work is directly proportional to the difference in the squares of the initial and final speeds. Take a second to pause this video here and write that down, sort of adding any part of this to your explanation that might have been missing, or just writing the whole thing down in general if you were a little confused about what this question meant. And when you hit play, we'll move on to part C. So part C is asking us to determine the change in kinetic energy for the baseball. And then part D is asking us for the total amount of work done on the ball. I hope you realize by answering part C, you've automatically answered part D, because according to basically what we just said here, the work done is equal to the change in total energy for the ball. And so that means the work done is equal to the change in the ball's kinetic energy. So by finding in part C the change in kinetic energy, we've automatically found the amount of work done. So let's go ahead and solve for the change in kinetic energy of the baseball. In order to solve for the change in kinetic energy of the baseball, and this is part C, you need the mass of the baseball, which is 0.160 kilograms. They told us in the problem it's 160 grams, and so you just move that decimal place back 3 places because kilo means 3. The final velocity of the baseball, once it's finally slowed down by the glove, is 0 meters per second. The initial velocity of the baseball, as given in the problem, is 40 meters per second, and we're looking for delta K. That's our unknown. So the change in kinetic energy is going to be the final kinetic energy minus the initial kinetic energy. And of course, because the ball stops once it's finally caught, it's finally slowed down by the glove, the final kinetic energy is 0. So that means the change in kinetic energy is just going to be the negative of the initial kinetic energy. Of course, it's going to be negative because if the ball is slowing down, it's losing kinetic energy. So that means delta K here is just going to be negative 1/2 mv squared, which makes this a pretty straightforward calculation. So we have negative 1/2 the mass, 0.160 kilograms, times the square of the initial velocity, so 40 meters per second, whole thing squared. And when you do that math, you get for your change in kinetic energy negative 128 joules. And that's it for the change in kinetic energy calculation. These calculations clearly are much easier when one of the energies, initial or final, is 0. And because part D asked us what is the amount of work done on the ball, well, according to the work energy theorem, the work is equal to the change in kinetic energy, so it's just negative 128 joules. Now, we've talked about this already in our notes, but I don't think we've ever solved a problem to this effect, so it's just important to mention here. Work can be negative. In this case, it is. All it means is that the energy the object had was lost. If work is a scalar, negative does not mean direction. The work in general means the change in the object's energy. So if the object gains energy, the work is positive. And if the object loses energy, then the work is negative. And that's it for part D. Now, moving on to part E. Part E is asking us to determine the force acting on the ball. And then part F is asking us about the force exerted on the glove. So let's get into part E first. In order to determine the force acting on the ball here, we need the work, which is negative 128 joules. We need the displacement, which is going to be 0.35 meters. We need the force, which of course is our unknown. Now, there are a couple of ways that you can look at this problem. The first way you could look at it is that you're solving for the magnitude of the force, and you don't have to worry about the angle. Or the second way is you can say the angle is taking care of the direction, but we're just going to ignore that and just solve for the force directly. Because this might be a little confusing, I'm going to show these side by side. The first way you could do it is you could just say work equals force times displacement. And that would give you the force is equal to the work over the displacement. And so that would give you negative 128 joules over 0.35 meters. And so that means our force is going to be negative 365.7 newtons. Now, of course, you could ask, well, why is the force coming out negative in that calculation? And there's a perfectly reasonable answer. The perfectly reasonable answer is that the baseball, let's just say in this picture, is moving to the right. And when the person puts the glove up, I'm not even going to try to draw that, so let's just say that's the baseball glove. When the person puts the glove up, the force that the glove exerts on the ball is like this, opposite the direction of the motion. And so because the force is opposite the direction of the motion, it's being counted as negative in this work. The other interpretation is to say, well, the force in this equation should just be the magnitude. That's actually how I originally introduced it to you. And because the force in this equation should just be the magnitude, the angle should take care of the direction. And if that were the case, the key thing to realize here is that these vectors are opposite. And that means the angle should be 180 degrees. And so you would have the work is equal to F delta X cosine theta. And when you solve that for F, you get the force is equal to the work over delta X cosine theta. And so that would give you negative 128 joules over delta X, 0.35 meters, times the cosine of 180. And the cosine of 180 is going to be negative 1. And so that means your force here will just come out as positive 365.7 newtons. Whichever way you do it is totally acceptable. It doesn't really matter. Both ways it's easy to see from the calculation what you are taking account of, what you are referring to in the equations, whether you say the angle is taking care of the direction or if the force is taking care of the direction. It doesn't really matter as far as this calculation is concerned. Both essentially lead you to the same and correct interpretation of the situation happening in the problem here. And so 365.7 newtons, whether you call it positive or negative, is the answer here for part E. And of course, for F is asking you about the force exerted on the glove. Notice this question here is asking for the force on the ball. Now we're being asked for the force on the glove. This is just a third law question, an action-reaction pair. So the force exerted on the ball, if it's 365.7, the force exerted on the glove is 365.7 in magnitude. And I'm just going to write in magnitude here because what you would refer to the sign as depends on whether you use the method shown here on the right or the method shown on the left. Everybody should be aware, though, that what we're saying here is not that complicated. The work done is producing this force, or I should say the force is producing the work. And this force, because the ball and the glove are interacting, is producing a reaction according to Newton's third law. We have equal and opposite forces exerted on each object. And that's it for part F and number 2 as a whole. Let's move on to number 3. Number 3 is one of these ranking tasks in the Tipper's book. This one is B4RTO5. It says cars that are moving along horizontal roads are going to be stopped by plowing into identical barriers. All of the cars are the same size and shape, but they're carrying loads with different masses. All the cars are going to be stopped by the same constant force by the barrier. That's a very important piece of information. It then says here, rank the distance that will be needed to stop the cars with the same force. There they've said it again, the force is the same. The basic idea behind this problem, once again, notice is a very important concept in this unit, is that the work is equal to the change in kinetic energy. And so that means the force times the displacement And again, we're not going to go nuts about the angle here. The force is going to be opposite the direction of the displacement. But either way, the angle here is just going to be contributing a negative sign, not actually a value. And so we don't really care too much about it. If you really want to include it, we can say cosine theta, and this is going to be -1. But since the final kinetic energy of all of these, because they're going to be stopped, is 0, essentially what we're going to have left over on the right-hand side is negative k naught. And that means this -1 is going to cancel that -1 over there, which at the end of the day is just going to leave us with F delta x equals k naught. So what this equation tells us is that when the force is constant, the distance that it's going to take to stop these cars is going to be directly proportional to their kinetic energy. And so really, the most basic way to solve this problem is to just solve for the kinetic energy of all the cars. You can't really base it on the highest speed per se, even though the kinetic energy is proportional to 1/2 mv squared, because it's dependent on both the mass and the speed. And so calculating this is really just the surefire way to do it. Most of the time I tell you not to do that. But for this one, it really is just about the most straightforward way you could answer this question. And so if you do 1/2 mv squared for A, you get 1/2 of 1,000 times 6 squared, which is 36, and that gives you 18,000 joules. When you do 1/2 mv squared for B, 1,600 kilograms, 1/2 of that, and then times 8 squared, that gives you 51,200 joules. For C, 1/2 mv squared, with the data given in this box, would give you 38,400 joules. And then for D, 1/2 is 1,600 times 16, because that's 4 squared, is 12,800. And according to the relationship that we teased out at the beginning here, the displacement is proportional to the largest initial kinetic energy. So that would make B the greatest, then C, then A, and then D. As far as the explanation is concerned, we can really just say this, what we said over here in the form of an equation. And so for the explanation here, we can write the work done on the car will be equal to the change in kinetic energy, or in the kinetic energy of the car. Since all cars have a 0 final kinetic energy, the largest initial kinetic energy will indicate the largest change in the kinetic energy. Since force exerted on each of the cars is the same, the greatest distance to stop the car for cars will be determined by the size of the initial kinetic energy of the car. And that's it. Take a second to pause this video here and write that down, adding any parts that you may have missing from your explanation to your explanation. And when you hit play, we'll move on to number 4. For number 4 here, which is B4RT08 from the same book, it says equal forces, work done on box. In the figures below, identical boxes of mass 10 kilograms are moving with the same initial velocity to the right on a flat surface. The same magnitude force F is applied to each box for a distance d as indicated in the figures. The question is saying rank the work done on the box while the box moves the indicated distance. To answer the question here, once again, the most efficient and straightforward way to do this is to use the equation. The work done on an object is equal to F delta x cosine theta. The part about this that may be confusing is that they haven't told us anything about the size of the force. Now, we could just make up a number and use that same number for all of the situations here, because they did tell us it's the same force in all of these situations. So like we could just make up a value for the force 1 Newton and do the math with all of the values given. But I think, as you'll see, we actually don't have to do that. According to this equation, work is equal to force times displacement times the cosine of the angle. The work is directly proportional to the force, directly proportional to the displacement, and directly proportional to the cosine of the angle. Also helpful to realize is that the cosine of 0, that's not supposed to be a theta, it's supposed to be a 0 degrees, is 1. The cosine of 90 is 0. And so here, looking at all of these diagrams, B is going to be the largest. How do we know? Well, it's the same size force for all of them, so that part doesn't really matter. But it's the largest displacement, and it's the only situation with this 10-meter displacement out of these two, B and D, where the force is parallel to the displacement the whole time. And because the angle between the force and the displacement is 0, that means the work is going to be maximized. So that means B is going to give us the largest work. The second situation, or the second largest work done, is going to be A, because it is the same size force, and the force is parallel to the displacement, but it's not as much distance as B. So A is next. Now we have to look at C, D, E, and F. But this is the part where it actually gets pretty easy. Because in D and F, the force is perpendicular to the displacement. And so that means the work done is going to be 0 joules in both instances. And in E, the force is opposite the displacement. And so that means the work is going to be negative. And so E is actually going to be last. And so filling in the rest of the rankings is pretty simple here. We have no idea what this angle is, but we know the fact that the force is raised up at some angle from the horizontal means the work is definitely going to be less than A, but it's definitely going to be bigger than 0. So C comes next, then D, which is equal to F because there's no work, and then E. Now, usually in class, and feel free to message me about this if this is confusing you, usually in class that is confusing to people why E is last. Notice it does not say anything about the magnitude here. It just says rank the work. And since the work in E is negative, it definitely comes last. In situations D and F, the object is neither gaining nor losing energy. But in E, the object is losing energy. It's moving at some initial velocity to the right, and there's a force acting on it to the left. And so, because the object is losing energy, it certainly has the least work done on it, as far as this ranking is concerned. And so, for our explanation here, there's really not a whole lot that we can say. We can just say this. The equations are the guides to the explanations. And that's a very important thing to remember, especially for this unit. And so we can just say the work done on the object, or objects, is equal to the product of the force, the displacement, and the cosine of the angle, which means the work is largest for the largest force acting along the largest displacement while acting parallel to the displacement. Take a second to pause this video here and write that down, adding any parts of this to the explanation that may have been missing. And when you hit play, we'll move on to the next sheet. Okay, moving on to sheet number 2 here. We'll go to the first problem, which says, how long will it take a 1,935 watt motor to lift a 400 kilogram piano to an 8th-story window 22.0 meters above the surface of the Earth? So in this question here, you're being asked how long. And so what we're looking for is the time. And so to solve this problem here, the first thing we're going to do is we're going to write down what's given. They told us the power of this motor is 1,935 watts. They told us the mass of the piano is 400 kilograms. They told us the displacement experienced by the piano is 22 meters, and that the time is what we're looking for. And so according to the reference table, the power is the change in energy over time. And really, from here on, there are two different ways that you can do this problem. The first way that you could do it is to say that the power is the change in the gravitational potential energy of the piano over time. Or you can say that the power is the work over time. Either way, you will end up with the same expression. If you use this version of the equation, the power equals the change in gravitational potential energy over time, you will end up with mg delta y, which we call delta x over here. So I'll write delta x over the time. Or you would end up with this expression. You would first write FD cosine theta over time. Now, of course, because the piano is being lifted straight up and is being lifted by a force, which also acts straight up, the angle here is going to be 0. And because the work that's being done here is opposing the force of gravity, at a minimum, this force here has to be equal to the weight of the object. And so you would end up with mg, I wrote d here, but that should be delta x, and then that's over the time. And so either way, you end up with the power is equal to mg delta x over the time. And of course, because we're looking for the time here, we can go ahead and solve this for time, and we get mg delta x over the power. And so that's going to give us here 400 kilograms times 9.8 meters per second squared. Of course, we did not include that up here, so we can go ahead and add it to our list. 9.8 meters per second squared is g. Then we multiply that by the displacement, 22 meters, and divide it by the power, which is 1935 watts. And when you do that math, multiplying all three of those numbers in the numerator and then dividing by 1935, you end up with 44.6 seconds, or to 2 sig figs, 45 seconds. It's important to realize here for this problem that because power in the reference table is listed as the change in energy over time, there are a lot of different forms that it can take, because you can write delta E over T, you can write W over T, you can write delta UG over T, you can write delta K over T. Any kind of energy that's changing can be listed in the numerator of that equation. Of course, also you can put the work and then you can transform that however you'd like using the equation F delta X cosine theta. And so there's a variety of problems that can be solved using this equation. This one would look like this. And that's it for number 1. Moving on to number 2. Question number 2 says a shot putter accelerates a 9.0 kilogram shot from rest to a speed of 12.0 meters per second. If her throwing motion takes 1.5 seconds, what is the average power developed by the shot putter? So, of course, to solve this problem, we'll write down the list of variables here. The mass of this shot put, as it says in the problem, is 9 kilograms. And they're telling us it's being thrown from rest, of course, when it's in the thrower's hand, to a speed of 12.0 meters per second. They tell us here as well that the time is 1.5 seconds, and we're looking for the power. So power here, as we were just mentioning a moment ago, is listed in the reference table as delta E over T. And because this shot put is being put in motion, the type of energy that is changing for this shot put is its kinetic energy. So we'll modify this equation and change it to write delta K over T. Now, of course, we can change that up yet again, because we can substitute in for delta K final kinetic energy minus initial kinetic energy. And we could, of course, divide that by time. And here, because the kinetic energy is 0 in the beginning, and we know that that's true because the velocity or the speed of the shot put is 0 in the beginning, then we can finalize this equation by writing k final over t. That's the ultimate form that this equation is going to take. Now, of course, we can make further substitution by writing an equation for the final kinetic energy in the numerator, which is going to be 1/2 mv squared over t, which, if you'd like, we could write as mv squared over 2t. Either way, it's the same thing, so it doesn't really matter which way you wrote it. And so to solve this for the power here, we just have to plug in. We have the mass of the shot put, 9 kilograms. We have the final speed, and we'll go ahead and write that as final speed just to make it consistent with the list of knowns. The final speed here is 12.0 meters per second, and we got to square that. And then we're going to divide that by 2 times the time, which is 1.5 seconds. And when you plug in those numbers and you do that math, you end up with 432 watts, which we can round here to 2 significant digits, 430 watts. And that's the answer to number 2. Now notice here, I decided to solve for all of this at the same time. If you chose to solve for the work or the change in kinetic energy separately, then you would have gotten 648 joules for the work. The work here being the change in kinetic energy would just be 1/2 mv squared. If you do that calculation, you get 648 joules. And when you plug that into power equals work over time, you end up with the same answer, 432 watts, or to 2 sig figs, 430 watts. And that's it for number 2. And with that, that's it for all of the calculations on both of these sheets. The last 2 situations on this sheet are conceptual questions. And so we'll take a look at those now here quickly before we wrap it up. Now, the first problem that's listed on the back of this sheet is number 3. B4CT48, race up a hill, work, and power. But I actually want to jump ahead here to number 4, just because number 4, whether you realized it or not, is actually a little bit of a simpler situation, and so it'll be a little more straightforward for us to discuss. And then, of course, having understood this example, we'll be able to better understand number 3. So this problem says Jason and Brent race up a hill that is 30 meters high. Jason takes a path that is 60 meters, while Brent uses a longer path that is 100 meters long. It takes Jason 40 seconds, while Brent runs up his path in a shorter time of 30 seconds. They both start from rest at the same height and stop at the top. Also, they have the same weight. A says, is the work that Jason does in going up the hill greater than, less than, or the same as the work that Brent does in going up the hill? And then B is asking us about the power. As you notice, whether it was in the examples that I solved in yesterday's video, or I guess the video that was posted on Tuesday, or this question, they love to ask you questions where they first ask you the work and then ask you to compare the powers generated in the situation. And so the first thing that we should note here is exactly how we are going to find the work. This could get complicated, but you can make it easy for yourself. In my view, the way to make it easy for yourself is to consider the fact that the work is equal to the change in energy. And in this instance, because they are running up a hill, the type of energy that is changing for them is gravitational potential energy. So if you decide to look at it that way, I think you'll have a much easier time. The reason why I'm telling you this is because if you choose to look at it using this equation, you've got a little bit of a problem on your hands, or at least the potential for confusion, because the person is following a curved path in this problem, kind of like an inclined plane, just with an angle that is constantly changing. And really, what you're trying to overcome when you're climbing up a hill is the downward force of gravity. And so the force that matters really is the force that's carrying them up the hill. Now, of course, because they're traveling along this curved path, that force would be continuously changing directions if you were going to consider the part of the force that is parallel to the displacement. It turns into a nightmare, in other words. And so this version of the equation is much easier to use. The reason why I'm saying this, of course, is because this problem goes through and makes the point of telling you the length of the path that they travel. And what I am telling you is that that does not matter. What matters here is the height of the hill, because the height of the hill determines their change in gravitational potential energy. And of course, the equation for the change in gravitational potential energy is mg delta y, and that's what matters. The problem says they take the same, they experience the same height change as they travel up the hill, and they have the same weight. And that's really all you know to be able to answer this question. And so we'll go ahead and we'll type for question A, at least the first thing we'll state is the answer. And we'll say the work done by Jason and Brent is the same, because the work done by each, we'll just call them students. We'll say they're studious individuals, because the work done by each student is equal to the change in gravitational potential energy. Since the gravitational potential energy is directly proportional to their masses and their height change, and they both have the same mass and experience the same height change, they both do the same work. Both of these individuals do the same work in climbing up the hill because the hill has the same height and they weigh the same. That ultimately is the key to the answer. Now, just before I ask you to pause this video here, we might as well just finish this thing up. Part B of the question, I'll just jump back to it for a second, asks, is the power generated by Jason in going up the hill greater than, less than, or the same as the power generated by Brent? Now, according to what we have seen so far and what we defined as the equation for the power, power is equal to the change in energy over time. We've already said the change in energy experienced by both of them is the same. So the relevant relationship here is that the power is inversely proportional to the time. And it tells you Jason takes 40 seconds while Brent takes 30 seconds. And so we'll write here for our answer, the power generated by Jason is less than the power generated by Brent. The power developed by each student is inversely proportional to the time they spend doing the same amount of work. Since the time taken by Jason is larger, the power developed by Jason is less. Now, it's important, before we pause here to take note of the answers, it's important to recognize that this sort of analysis, that more time means less power, is only true when they do the same work. In this instance, because they do the same work, that analysis is acceptable. Take a second to pause this video here and write that down. And when you hit play, we'll move on to the last question on the sheet, number 3. And that brings us to the last question on the sheet here, number 3. Number 3, notice, is a very similar situation, but there's a slight modification to the problem that makes this a little bit more difficult. It says, Abby and Bonita decide to race up a hill that is 30 meters high. Abby takes a path that is 60 meters long, while Bonita uses a path that is 100 meters long. It takes Abby 40 seconds because her route is steep, while Bonita runs up her path in 30 seconds. They both start from rest at the same height and stop at the top. Abby has a weight of 700 newtons, and Bonita has a weight of 500 newtons. So it's important to realize here, the situation is very similar because we are going to use the exact same analysis to compare the amount of work that's done by each person. But of course, the result of that analysis is going to be different because the potential energy gained by each person, if we're talking about that being equal to the work, the potential energy being gained by each person is going to be different here because they weigh a different amount. And so what we can write here for this answer, for part A, is the work done by each student is equal to the change in gravitational potential energy, which is proportional to the mass of each student and their height change. While each student experiences the same height change, Abby has a larger weight and thus a larger mass, since Fg equals mg, and so more work is needed for her to reach the top of the hill. Notice, very similar analysis, but a different different conclusion, because now that they no longer have the same weight, a different amount of work is done. Now, this is not the complicated part of this problem. The complicated part of this problem comes in part B. Because in part B, it says, is the power generated by Abby going up the hill greater than, less than, or the same as the power generated by Bonita in going up the hill? And the real way to answer this question comes from thinking about the equation and comparing the values of their weight and the values of their time. Notice it says here that Abby has a weight of 700 newtons, while Bonita has a weight of 500 newtons. That means Abby's weight, and thus Abby's work, and so I'll write this down here just to keep track of it. Abby's work, the work of Abby, is going to equal 1.4 times the work that Bonita does. That's because her weight, 700 newtons, is 1.4 times larger than Bonita's weight. However, according to the text of the problem, the time that Abby takes is 40 seconds, while the time Bonita takes is 30 seconds. And 40 is only 1.3 times bigger than 30. And so Abby's time is 1.3 times bigger than Bonita's time. And so if you thought about putting this into the power equation, work over time, thinking about this being the equation for Bonita, and then plugging in sort of like in a 1-1-1 rule style for Abby, you would put a 1.4 in the numerator and a 1.3 for the time in the denominator, and that would end up giving you a power that is 1.07 times larger for Abby. And so there are a lot of ways that we can explain this here, but the most coherent explanation would probably look a little something like this. We could say power is proportional to the work done and inversely proportional to the time. The work for Abby is greater by a factor of 1.4. We could say although the time it takes for Abby is only 1.3 times larger than Bonita's time, the work she does is 1.4 times larger, which means the power she develops will be larger than the power developed by Bonita. And that's it for number 3. Sometimes it's important to think about ratios and how the power, or in this case, the work and the time, compare separately before you try to put it together and answer a question like this. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, that's it for today. And that's really it for the general introduction to work, power, and energy. In the next couple of videos, we'll be talking and thinking about how energy flows within a system, specifically conservation of energy. All right, everybody. Have a good one.